Good afternoon, good people. Forgive me, I see you guys at the end of a day that begins very early, and I'm talking like this at the computer constantly, so my throat is quite sore. But today is our first day after the exam, and I want to congratulate you guys on doing a really wonderful job on the test in every way. The procedural stuff went really well. I saw everybody getting in and taking the test right on time. I didn't have any like, holy shit, I can't make any of this work emails. A few people had a little bit of trouble getting cam scanner, getting PDFs where they needed to be, but everybody did a good job communicating with me. And so again, yeah, just thank you for the preparation and the work you put into making that go smoothly. I'll have your exams graded by Wednesday. I don't have them graded yet. Of course, the true, false, and multiple choice are graded automatically, but I just got my fancy new tablet, so I can get in there and annotate the PDFs you sent me directly. So I will have those grades in for you on Wednesday, and we can discuss the exam then. But we do have a lot to cover this week. This is the beginning of the more technical part of the course. So up through now, most of the work we've done has come from like looking at a graph and making some observations, knowing definitions, that sort of thing. But beginning today and through the rest of the course, this is very much a technical skill-based course where you're going to learn to do shit algebra-wise. So be warned, the course is kind of changing tack a little bit here. Those concepts are all still going to be hugely important, and I'll still ask you those same sort of questions, but now you're going to have to come up with the graph. And the main portion, or the main emphasis on this portion of the class is to get you to a place where you understand functions well and can graph them readily on your own without any graphing utilities. So today, we begin the middle third of the course, which is a detailed study of functions or function types. In particular, starting with polynomials. You would be forgiven for thinking, coming out of college algebra, that you know everything about polynomials that you ever needed to know. But the truth is far from that. In fact, polynomials are a massively complicated family of functions. So much so that even though I dedicate a big chunk of this class to teaching you the algebra of polynomials, I could spend another 5 or 6 classes telling you beautiful things about polynomials and teaching you how to work with them in ways that you could never imagine. The research that I did in graduate school is loosely related to the study of polynomials in a handful of ways. I just want to say that it turns out that if you study polynomials as an algebra structure on their own, like you think about the set of all polynomials and the sort of things you can do with them, it is a wildly rich space. If you've ever heard of a vector space, you know that polynomials form a vector space. But what's more, they form a commutative ring. You can form quotients out of them. You can do all sorts of really fantastic things with polynomials that you may have never heard of before. So today, my goal is to do a handful of things. I want to prove for you the quadratic formula. Function types. So the middle third of the course, which is a detailed study of function types, starting with polynomials. we're going to learn how to complete the square. And we're going to use that to prove the quadratic formula. We're going to talk about graphs of quadratic functions, which hopefully is review. And then we're going to start talking about polynomial factors. How they connect with roots. Some people call these solutions, although that's a little bit dangerous. And we're going to talk about the degree of polynomials and end behavior. So you're also going to learn a little bit of calculus notation. I'm going to introduce the concept of a limit to you guys today, if we get through all the other things. So that's quite a lot. And this is most of what we're going to be doing this week. Next week, we're going to talk more about polynomials. If you look in the syllabus, division of polynomials is also a topic for this week. I suppose I should write that down there. But the section on dividing polynomials is long, and I'm going to split it up. So we're going to talk a lot about polynomials, their graphs, all the things I just listed, and a little bit about dividing polynomials. But that connects gloriously with the rational roots theorem and all of these other things. So this will be half this week, half next. Okay, so let's dive in. Quadratic functions. This should be mostly review. There's a little bit of vocabulary here that's a bit different. So a quadratic function f of x is one which can be expressed as f of x equals ax squared plus bx plus c. We call a the quadratic coefficient or lead coefficient. We call b the linear coefficient. And we call c the constant term or constant coefficient, but sometimes just called the constant term. Normally, this is what people call the standard form, but your textbook doesn't call this the standard form. Your textbook calls what usually we call the vertex form as the standard form. So first off, this is the definition, right? A quadratic function is any one that you can write like this. And I'm going to use the language of the textbook here, even though it's not sort of the normal language, the quote-unquote standard form. Other places call this vertex form. Of a quadratic function is f of x equals a times x minus h squared plus k. Yeah, expressed. Expressed is the word that comes after the word b in the first one. All right. So I'm thinking probably everybody has seen these before. We know their graphs are parabolas. They have this neat little bowl shape. It's not really a theorem, it's just a fact. I'll state a few of them here. Graphs of quadratic functions are parabolic, meaning they are parabolas. If the lead coefficient A is positive, the parabola opens upward. And if A is negative, the parabola opens downward. So, you know, this would be A is positive. And something like this, A is negative. I'm thinking probably everybody has seen this before. The reason this is called the vertex form usually is because the point here, or in this picture, the point here is always h comma k, where h and k are those numbers from the standard form. The x-intercepts here, and x-intercepts for any polynomial in quadratics are a special polynomial of degree 2. We'll talk about that later. The x-intercepts of a quadratic can be found using the quadratic formula. And now, ladies and gentlemen, we are to a place where I, for the sake of your education, will do something shameful. I will show you how to never ever forget the quadratic formula. And we're going to prove it. And that usually is sufficient, but I feel bad if I don't do this. I feel bad if I do it. So we all remember the tune, Hop Goes the Weasel. You can sing the quadratic formula to that tune. And what I'd like you to do is find someone you respect deeply, like your partner or a close friend or a parent. Stand before them and sing x equals negative b plus or minus the square root b squared minus 4ac all over 2a. It's horrendously embarrassing. Easier to do online. I'm not really blushing. When I do this in person, it's bad. But that will help you remember this. You must remember this. Not only this class, but many classes after this will make use of this. And what I'm going to do for you now in addition to embarrassing myself like that by saying, is prove this for you. That's very sweet of you to say, Matthew. I know it's not true. We complete the square. So before I complete the square for you, in the general expression, I would like to show you how to complete the square in a few special cases. So do me a favor. Leave at least a page, probably more like a page and a half. I intend to use the rest of this space and the whole back of this paper to prove this formula. It's going to take a minute. In order to help you follow it, I want to give you some practice in completing the square elsewhere. So leave a page and a half in your notes blank. And then we're going to talk here about how to complete the square. This is important now, and it will also be important later when we talk about conic sections. So I'm introducing it because we need it for the proof, but also we will need it later in the semester. So please give a page and a half of blank space in your notes, and then after that blank space, write how to complete the square in a quadratic. So the quadratic is ax squared plus bx plus c. First, what you do is you make the coefficient of x squared equal to 1. So, for example, if I had something like 2x squared minus 4x plus 6, I would factor out the 2. And now here, the coefficient of x squared is 1. Your second step, after you've divided out by whatever number is in front of x squared to make sure that the x squared has a 1 in front of it, next you compute what I'm going to call the magic number, which is b over 2 all squared from this form. So in this example, my magic number would be -2 over 2 all squared, which is -1 squared, which is 1. Your third step is you add and subtract the magic number after the x term. So right after this 2x, I'm going to add 1 and subtract 1. So my whole thing now looks like 2, open parentheses, x squared minus 2x plus 1 minus 1 plus 3. And then your fourth and final step for completing the square, factor the first 3 terms as a perfect square. So here that would look like 2 times, here's my first 3 terms, those factor as a perfect square. That's x minus 1 times x minus 1. So that's x minus 1 all squared. And then you've still got this minus 1 plus 3. You still have your 2 outside. And then you can simplify. This isn't really a part of completing the square. We have completed the square. But now I can combine the -1 and the 3 and then distribute the 2. So I've got 2 times x minus 1 all squared minus 1 plus 3, that's plus 2. And now when I distribute the 2, I get 2 times x minus 1 all squared plus 4. The result is a quadratic in vertex, or according to your book's language, standard form. So I can tell you where the vertex is. I can tell you whether the parabola opens up or down. And those two things will allow me to get a really nice graph. So this is completing the square. And what it does is it takes you from like ax squared plus bx plus c to a times x minus h squared plus k. Right, this is a times x minus h squared plus k. So for this guy, a is 2, h is 1, and k is 4. Be aware that there's a negative sign built into this formula for standard form. So it's always x minus h squared. So this x minus 1 tells me h is actually positive 1. Completing the square is useful for lots and lots and lots of reasons. First and foremost, it lets you go from this form to this form. Hard to graph from the original ax squared plus bx plus c. Easy to graph from a times x minus h squared plus k. So it's useful for graphing. Notice that this lets me think of it as a transformation of y equals x squared. This is y equals x squared shifted to the right 1 unit, vertically stretched by a factor of 2, and then shifted up 4 units. Nice, right? So now that we've done an example of this, kind of long, I'm going to do another example fast, and then I'm going to prove the quadratic formula for you. First though, any questions on any of these steps? So step 2 says compute the magic number, which is b over 2 all squared. So there's no capital A's here. Is that what you're asking? Okay, yeah. This is a b. All right, let's do another quick example. So we're going to complete the square in f of x equals, how about 2x squared plus 6x minus 4 to write in standard / vertex form. Then graph. I have no idea what the roots of this thing are. I want to complete the square. So 2x squared plus 6x minus 4. First, I factor out the 2 to make the coefficient of x squared 1. That'll give me x squared plus 3x minus 2. Now my magic number is b over 2 all squared, which is 3/2 all squared, because b there is 3 in my simplified guy. And this is 9/4. Then I add and subtract my magic number right after the x terms. This is x squared plus 3x plus 9/4 minus 9/4 minus 2. Now I want to factor the first 3 terms as a perfect square. And the good news is it's always going to factor as x plus or minus this thing squared. So those first 3 terms factor as x plus 3/2 squared. You can check this. I need 2 numbers that multiply to 9/4 and add up to 3. Well, 3/2 times 3/2 is 9/4. And 3/2 plus 3/2 is 6/2 is 3. So those first 3 terms factor like this. And then this stuff is just coming along for the ride. So I've got my minus 9/4 minus 2. And now I just simplify. So this is 2 times parentheses, parentheses, x plus 3/2 squared. And then minus 9/4 minus 2. Well, minus 2 is, so I'll do it over to the side. Minus 9/4 minus 2 is minus 9/4 minus 8/4, which is minus 17/4. So here I have minus 17/4. And then I can distribute the 2. (17/4) times 2 is 17/2. And that's it. I have completed the square. This is the thing your textbook calls the standard form. So here h and k can be read off. K is always this number, taken with whatever sign it has here. So minus 17/2. H is always this number, taken with the opposite sign it has here, because remember the formula has x minus h. So h is negative 3/2. And A is always just the number out front. It's always the same as the original lead coefficient. I got the 17/2 by taking negative 9/4 and subtracting 2. I did the arithmetic off to the side here. So 2 I write as 8/4, and then negative 9 minus 8 is negative 17. So I had to subtract these. I did that off to the side here, and then just wrote the result here. Are we comfy? So the last thing we wanted to do is graph this. I know that my parabola is going to open up because A is positive 2. And I know my vertex is at -3/2, comma, -17/2. So I'm going to give myself some space on that side. I'll mark this as 1, this as -1, and this as -2. -3/2 is -1.5. So that's right in between -1 and -2. -17/2, let's see, 16/2 would be 8, right? So 17/2 is 8.5. So I'm gonna come down here, I'll mark this as like 8, and this is like 9. So my h comma k, my vertex is right here. -3/2, comma, -17/2. I know the scale on the vertical axis is wonky. And then my parabola opens up. All right, this would be a perfectly acceptable graph for these purposes. We've got the vertex correct. We've got the parabola opening in the correct direction. For now, this is good enough. Do we understand where the 17/2 came from? It's not super obvious. I know that this arithmetic here is a little wonky and we got to get comfy working with fractions. There's no escaping it in pre-calc. We can't calculate our way through fractions using decimals and the frac button. We got to do it. I'll leave this here for another second. Is there any questions? I would like to hear them. Okay, so now we're ready to prove the quadratic formula. I distributed this 2. So the 2 has to get distributed here and also over here. So the -17/4 is the correct value when you subtract 9/4 and 2. And then when I distribute this 2, that'll slap a 2 here, and it will also slap a 2 here. And 2 times this makes that denominator a 2. Okay, cool. I'm glad. That makes me feel much better moving on. Any other questions? It's good. Don't feel weird at all about asking questions. It's a totally new thing. You're supposed to be a little bit puzzled by it. I'm supposed to answer your questions, so please ask them if you have them. Everything else feels good? All right, then we're gonna go for it. We have to take our fully general f of x equals ax squared plus bx plus c and complete the square. So my first step is to make the coefficient of x squared 1. That means I need to factor out an a. That will give me x squared plus b over a times x plus C over A. When I factor out this A, I have to divide every single piece by A. That does what I wanted. It makes the coefficient of x squared equal to 1, but it also introduces these fractions. Okay, so we're going to have to just be brave. Now I compute my magic number. I know that this means hashtag to you guys now, but it used to mean number. You take this guy, divide him by 2, and then square it. So that's b over a, all divided by 2, squared. That's b over 2a squared. Which is b squared over 4a squared. Now I take that magic number and I add it and subtract it right after the x term. So this is a, open big paren, x squared plus b over ax plus b squared over 4a squared minus b squared over 4a squared plus c over a. And then I take these first 3 terms here and I factor them as a perfect square. So x squared plus b over ax plus b squared over 4a squared, that factors, and the rule is always it'll factor as x plus or minus one of those two, this guy, depending on the sign in here. So that factors as x plus b over 2a squared. And then I still have these guys, minus b squared over 4a squared plus c over a. And in a second, you're going to start seeing some familiar pieces from the quadratic formula show up, like b over 2a, b squared minus 4ac, all that good shit. I'm going to continue over here so I can make good use of this space. So dot, 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 dot. I'm going to simplify now. So this is x plus b over 2a quantity squared minus. I want to combine these two. So I'll have a common denominator. That means I need to multiply this guy by a over a, and I need to multiply this guy by 4. Oh, let's see. No, he already has an a, doesn't he? Yeah, he doesn't need anything. So b squared over 4a squared plus, this piece though needs to be hit by 4a upstairs and down. So that's 4ac over 4a squared. And now we're almost done. Now that these have a common denominator, I can put them together. It's important to remember that this b squared term is negative. So when I put those together, I'll have x plus b over 2a squared. Change this to plus 4ac minus b squared. Maybe I'll write it as plus negative b squared plus 4ac all over 4a squared. We can write it like that. I think that's probably what makes most sense given what we had in the previous line. Remember what we're trying to do. We're trying to find the x-intercepts. And this is f of x. Therefore, f of x is equal to 0. Those are how you find x-intercepts, provided this shit is equal to 0. So here's our second page starting. Provided a times parentheses x plus b over 2a all squared plus negative b squared plus 4ac all over 4a squared is equal to 0. My next step is to divide both sides by a. 0 divided by a is still 0, so I get x plus b over 2a squared plus negative b squared plus 4ac all over 4a squared is equal to 0. Now I'm going to subtract this whole term over to the other side because I want to solve for x. Remember, the quadratic formula is like x equals. So what we're trying to do with all of this is solve for x. We set f of x equal to 0 and then solve for x. So now I subtract that term to the other side and I get x plus b over 2a squared equals negative b plus 4ac all over 4a squared. Like this. I can distribute that negative. And I get b minus 4ac. Sorry, b squared. That's a b squared in that previous line. I dropped the square. I'm so sorry. B squared minus 4ac all over 4a squared. You're starting to see the quadratic formula appear. Finally, I'm going to take square roots on both sides. So I take the square root over here, and I take the square root over here. I get a plus minus. Like this. The square root and the square cancel on this side. And I can simplify the square root here too by giving it to the top and bottom separately. The square root of the downstairs is the square root of 4, which is 2, times the square root of a squared, which is a. And now I subtract b over 2a from both sides. So x equals negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, which you can combine into a single fraction because these are common denominators. So this is equivalent to the normal quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Proof is complete. Pretty badass if you ask me, but I'm a mathematician, so my opinion may differ from some others. But I don't know how many of you have ever seen this. I think probably most people go their whole lives memorizing this formula, but never ever knowing where it comes from. Now you are a cut above the rest. No, you're not. you will have to complete the square, but not with all these symbols. You'll do it just like I did in that last example with the numbers. So I could give you a quadratic formula or a quadratic function, sorry, like 3x squared minus 5x plus 7, and say complete the square and then graph. But this proof of the quadratic formula is purely for enrichment. All right. Sorry to scare you. There's a deeper reason why I do this, though. Think about the graph of a quadratic function. Looks something like this, right? And you know that the vertex down here, this is h comma k. So there's two roots. Call him x1 and x2. Do you see any symmetry in this graph? It's symmetric about the vertex. In particular, this distance and this distance are the same. If the two roots, x1 and x2, come from this formula, and I like to think about it like this rather than like this, if the two roots, x1 and x2, are the two numbers output by this formula, then this has to be the vertex, because it says start here and go to the right. That's the plus, some amount. Or start here and go to the left, some amount. So this distance right here has to be the square root of b squared minus 4ac over 2a. And so does this guy. Which means this guy right here has to be b over 2a. So when you think about the quadratic formula like this, here's your vertex, and here is how far you have to walk left or right from that vertex to get to the roots. These, whether you take the plus or the minus, are always the same size. So the roots are evenly distributed about this x value, which means this x value has to be the axis of symmetry, and that's how you get your formula for h. So by symmetry and the quadratic formula, h is always, I'm sorry, negative b over 2a, yeah. Negative b over 2a. People find it useful to remember this. Please take a moment. Make sure you have our proof of the quadratic formula, at least this line. All right, if you got lost in the proof, don't panic. You can leave space in your notes, come back and fill it in. There's a million places you can read this online, but please make sure you have this and this nice and clear in your notes. And I want you to study that picture and understand the geometry. This says to find your x-intercepts, start here and go to the right, that's the plus, this amount, and also go to the left, that's the minus, this amount. So this version of the quadratic formula tells you more than just the x-intercepts, it also tells you the vertex, and that's a big deal. The parabola is symmetric about the vertex. So the place where you're starting and then walking left or right has to be h, has to be the x coordinate of this vertex. If there's one new thing I hope you learn about quadratics from this course, it is that interpretation of the quadratic formula. Completing the square is good. You're going to need it here when we talk about quadratics. You're going to need it here when we talk about conic sections. You're going to need it all over the place in Calc 2 when you talk about trig sub. So that procedure is important. Going through it with all the symbols A, B, and C, not as important, but a good exercise. And it shows you where the quadratic formula comes from. I think that's beautiful. But more than anything, I want you to interpret the symmetry in this formula and how it relates to the symmetry in this picture. I know a lot of you memorized h equals negative b over 2a to get through college algebra, but did anybody ever tell you why? This is why. Okay. I don't want to drum on too much more about quadratics. I know you guys have played with them. I'm confident that you know how to find the roots and find the vertex and factor them. If you forget how to do any of that, please go back to your old notes and remind yourselves, because what we want to talk about next is polynomials in more generality. How am I doing on time?
Wait, I have a question. Is h equal negative b over 2a? Like, doesn't it have a specific name?
Yeah, that's the x-coordinate of the vertex.
Okay.
That's h from the vertex formula. This vertex always has x-coordinate h equals negative b over 2a. And it is a direct consequence of this. That's kind of what I was trying to point out here.
Okay.
So in your vertex form, in the thing that your textbook for this class calls standard form, the a times x minus h squared plus k, h is always negative b over 2a. And you can always find it by completing the square, but that can be a little tiresome. So I wanted to show you this derivation. Does that answer the question?
Yeah.
Okay, cool. All right. So you've now seen from a higher level all of the quadratic stuff that you learned and messed around with in your baby algebra classes. Now we're in big boy algebra. Polynomials in general are a little more complicated. So section 3.2, we're talking about graphs of polynomials. There are a bunch of theorems here. There are a bunch of rules, and your factoring skills need to be strong. I'm going to begin by discussing a few basic functions. I guess first the definition. First, basic polynomials. These are monomials. Functions like x to the n. You know what x squared looks like. You know what x cubed looks like. Do it here. X to the 4 is like a flattened out version of x squared. It's like someone came in and squished x squared down harder on the x-axis. X to the 5 is like a flattened down version of x cubed. And the pattern continues like this. X to the 6 is a flatter still version of x squared. and x to the 7, and so on, right? All higher order or all more complicated polynomials are built out of pieces that look like these. So I'm going to give you the general grown-up definition of a polynomial. It's going to look a little bit scary, but I want you to be brave, write it down exactly as I write it, and then we'll discuss the names of each piece and where each piece comes from. Leave some blank space here in your notes or somewhere nearby these graphs so we can talk about end behavior. And if there's time, we'll get to that today. Otherwise, we'll have to push it to Wednesday. Built. Oh, I left off an L. Built. B-U-I-L-T. Thank you. So the kind of business with the higher the power, so maybe I'll write that here. The higher the power, the flatter the graph is near the x-intercept. Pieces. So all more complicated polynomials are built out of pieces that look like these. Meaning like combinations of whole number powers of x. But yeah, all more complicated polynomials are built out of pieces that look like these. And the higher the power, the flatter the graph is near the x-intercept. So here with x squared, the graph is kind of rounded, kind of curvy near the x-intercept. Here with x to the 4, the graph has been flattened out near the x-intercept. And here with x to the 6, it's almost totally flat near the x-intercept. And you see the same thing with the odd powers. It's just that they point up on one side and down on the other instead of up on both sides. This has to do with what are called multiplicities. And we're going to talk about multiplicities a little bit later. All right. So here's the grown-up definition of a polynomial. A polynomial of degree n is an expression of the form an, the little n down underneath the a, it's called a subscript, times x to the n plus a n minus 1 times x to the n minus 1 plus, and then this goes all the way down to a1 times x to the 1, which is just x, plus a0. Here, an is non-zero. And all the other a's, let's call them ai, because they can be a sub whatever, are real numbers. or let's just say numbers. So all the AIs, you don't need the word other too, all AI are numbers called coefficients. Coefficients. So coefficient is just the name for the number that multiplies a power of x in the polynomial. The degree is the largest power of x that shows up anywhere in the polynomial. And the reason we say an is not 0, because if an was 0, then this term wouldn't really be here. The subscript on the second a is n minus 1. So the subscript always matches the power. That's the idea. The subscript identifies the power of x to which that coefficient is attached. So it's an x to the n minus 1, x to the n minus 1. The next term would be an minus 2 times x to the n minus 2. And we continue, that's these dot, dot, dots. That pattern continues just like that until you get down to a1 times x to the 1. And then a0, and you can think of there as being an x to the 0 here, but remember x to the 0 is just 1. So we just write a0. The coefficient an is called the lead coefficient. And a0 is called the constant term. Okay, so that's the full grown-up definition of a polynomial. And we'll look at some examples to make sure we're comfy with the naming conventions. This is a polynomial of degree 3. Because the largest power of x anywhere is 3. Even though this is a square root of 5, the thing is still a polynomial. I should say here that n has to be a positive integer. Sorry. Whole number. So only whole number powers of x. Here, in this example, a3 is the lead coefficient, and it is 7. a2 is negative square root of 5. a1, I don't see any plain x terms here. So a1, the number that would normally just be multiplying x, here is 0. And a0 is 4. So the lead coefficient here is 7, and the constant term here is 4. If your function has any powers of x that are not non-negative integers, like fractional powers of x, square root of x, x to the 1/2, x to the 2/3, that's not a polynomial. And anything that contains those is not a polynomial. Any function that has a negative power of x is not a polynomial. But this guy does fit this definition. This is a3 times x to the 3 plus a2 times x to the 2 plus a1, which is 0, times x plus a0, which is 4. Correct. So there's our little example note. If a function contains powers of x which are not positive or not whole numbers, not integers, then that function is not a polynomial. So yeah, having negative powers of x or having powers of x which are not whole numbers kills the polynomial definition. So polynomials are like the function version of whole numbers. And accordingly, the powers of x in a polynomial must be non-negative whole numbers. Okay, so the game, is this a polynomial or is this not a polynomial, is not super exciting. You just look to see if it satisfies the definition. You look to see if it has only positive whole number powers of x added up with some coefficients. What is exciting is starting to talk about factoring polynomials and the connection between roots and factors. There isn't really time for me to get into that today. But what there is time to do is to talk about end behavior. So that's the last thing that we're going to do. Does anybody need more time on this page? If a function contains. If a function contains powers of x which are not positive or not whole numbers, then that function is not a polynomial. So polynomials have to have just positive whole number powers of x, like x cubed, x to the 5, x squared. All right, so I'm going to wrap up here today by talking about polynomial end behavior. By end behavior, what we mean is how the function behaves for very large values of x. If a polynomial has even degree and a positive lead coefficient, then on either side, as you go off really far to the left or really far to the right, the graph will go either up on both sides or down on both sides. So this is the picture that corresponds to an even degree and a positive lead coefficient. So if I give you a polynomial and the degree is even and the lead coefficient is positive, then I can't tell you what happens in between here. All sorts of complicated shit could happen in between there. But I know that the graph goes up eventually on the left and goes up eventually on the right. The way we express this is we say as x goes to negative infinity, this is as we wander off to the left, y goes to positive infinity. And as x goes to positive infinity, as we wander off to the right, y also goes to positive infinity. We go up. So you can read this as we go to the right, really, really far, the y values end up going up. And you can read this as we go to the left, really, really far, the y values end up going up. If you have an even degree and a negative lead coefficient, again, I can't say what happens in the middle, but I can say that the end behavior picture has to be flipped over. So this is the picture that corresponds with even degree and a negative lead coefficient. And the goes to notation, we say as x goes to negative infinity, or as we wander far off to the left, the y values go down. So we'd say y goes to negative infinity. And as x goes to positive infinity, y goes to negative infinity. So your kind of basic examples that you can think of here, this is like y equals x squared. I don't know what happens in the middle, but I know it goes up on both sides because the degree is even, 2, and the coefficient is positive, 1. Your kind of basic example here is like y equals negative x squared. I don't care what happens in the middle, but I know on both sides, if you wander out far enough, it goes down. And any polynomial of even degree with a positive lead coefficient will have this same end behavior. Any polynomial with an even degree and a negative lead coefficient will have this end behavior. What we're going to do on Wednesday is try to figure out what's going on in the middle. That's much, much harder. But for now, we're just talking about the end behaviors, like how the arrows point on the far edges of the graph. And then for odd degree, there's again 2 cases corresponding to positive and negative coefficients. If you have an odd degree and a positive lead coefficient, again, I have no idea what goes on in between. Oh, sorry, odd degree and positive lead coefficient. The goes to notation here is as x goes to negative infinity, y goes to negative infinity. That's this arrow. As we wander really, really far out to the left, eventually we're going to go down. And as x goes to positive infinity, y goes to positive infinity. And every polynomial whose degree is odd and whose lead coefficient is positive will have arrows at the end like these. Finally, if you are an odd degree and you have a negative lead coefficient, things will be flipped over. You might do all sorts of crazy stuff in between, but eventually, oh shit, you're gonna do something like this. So again, here we're just discussing the end behavior, just the arrows at the very end of the graph. If you are odd degree with a negative lead coefficient, then as x goes to negative infinity, y will go to positive infinity. And as x goes to positive infinity, y will go to negative infinity. This goes to notation, the arrows, you're going to be seeing that in your homework, and you need to play with it and get comfy with it. But the rules are just these rules. They're actually very simple. Don't be intimidated by the infinity sign. Think of x goes to negative infinity as just saying, as we go really far to the left. And y goes to plus infinity means, oh, well, that arrow points up. And similarly for all the rest of these guys. So figuring out what happens at the ends, that's not hard. Figuring out what happens in the middle, that's the challenge. And what we're going to start talking about next time is how to figure out where these x-intercepts come from. You know that with quadratics, it comes from factoring. And the same thing is true here. It's just that the rules for factoring higher order polynomials is much, much harder. I'll be able to give you some tricks that work pretty well. But in general, this is a problem that not only is hard to solve, but mathematicians have proven that it cannot be solved. If you have a polynomial of degree 5 or greater, there's no guarantee that you can find the x-intercepts with a formula. Sometimes you can. Sometimes you can factor them. Sometimes there are tricks, and I'm going to show you all the good tricks. But it was a result due to Évariste Galois, a famous 19-year-old French mathematician who died in the French Revolution, tragic stories, proved that there is no formula for the solutions of a degree 5 polynomial equation in terms of the coefficients. So we can't hope to come up with something like the quadratic formula for big polynomials. But there are things we can do, and it starts with factoring. So next time on Wednesday, I'm going to start showing you how to factor big polynomials, how those factors correspond to x-intercepts and the shape of the graph near those factors. That information, together with the information we have about end behavior, will be enough to sketch really nice graphs of these polynomials. And then we're going to talk about details like how many turning points a polynomial graph can have, how that relates to the degree. And then we're going to start talking about dividing polynomials, which will be where we get some of those neat tricks for finding roots. So this is where I'm going to leave it for today. Thank you guys for hanging out. I know I went a few minutes over. Lily asked a good question. So is there any way to improve an exam score? No, unfortunately, the exam scores are what they are. But what we do is the final can replace, right? Yeah, so if one of your midterm tests is an absolute bomb, the final will replace your lowest test score if it improves your grade. So that is what we have. And no, it's okay. Don't stress about asking the question. It's a good and fair question. So yeah, if the final is higher than your lowest midterm exam, I will replace your lowest midterm exam score by the score on the final. But there aren't anything like rewrites or retests or anything like that. Again, I'll have your test graded by Wednesday. And that is it. This is where I'm going to leave you guys for today. You can come by office hours if you want to talk about anything. Otherwise, I'll see y'all on Wednesday. All right. Take care, guys.